Hello, discrete math fans. Now I'd like to talk about the well-ordering principle. This is a statement about natural numbers. And although it looks nothing like our two principles of mathematical induction, it turns out that all three statements are logically equivalent, in the sense that you can prove each one from the other. Now that's actually an interesting statement because it also says that the two induction theorems are not any stronger than each other. So strong induction is not actually any stronger than weak induction. It's not a more powerful theorem. It's a more useful theorem in certain contexts, but it doesn't give you any more power. So here's what the well-ordering principle says, and we're going to take this to be an axiom, which means it's a truth that we just accept about numbers or about logic that we don't prove, we just accept it to be true. Let's let S be a non-empty subset of the integers, all of which are greater than some fixed integer. All right, so your set has to be non-empty, and everything in that set has to be bigger than some fixed integer. So maybe there's 13 things in the set, and they're all bigger than some particular integer. The conclusion of the well-ordering principle is that S has a smallest element. Now, we should note that not every subset of the integers has a least element. Think about the set of odd integers. This does not have a least element. The values keep going down forever. Now, this does not contradict the well-ordering principle, because the principle says that all of the elements of your set has to be larger than some fixed integer. Well, that's not true here. The set of odd integers has no such lower bound. All right, what about this set of positive real numbers? Now, that does not have a least element. Now, this also does not contradict the well-ordering principle. Now, the set of positive real numbers, it does have a lower bound, but the well-ordering principle only applies to subsets of the integers. Now I'd like to give you a situation where we can apply the well-ordering principle. And I want you to remember the quotient remainder theorem. All right, this was how we stated the quotient remainder theorem. Given any integer n and a positive integer d, there exist unique integers q and r such that n is equal to dq plus r, and the value of r, our remainder, has to be bigger than or equal to 0, but still less than d. I'd like to prove part of this theorem, namely the existence part, the part that says that there exist these integers q and r that satisfy these properties. And at the moment, we won't address the uniqueness portion of this theorem. All right, so here's our proof of existence. Let's define S to be the set of all non-negative integers that look like n minus dk, where k is an integer. So what you do is, remember that n and d are given, and you look at everything that might look like this, n minus dk. K can be anything you like. And you take all of those possible things and only include the things that are non-negative. And that's what's going to go into S. Now I'd like to apply the well-ordering principle to the set S, but in order to do so, we have to prove two things about S. First, it has to be non-empty, and second, it has to be a subset of the integers that's bounded below. Well, the second part is easy. It's created from non-negative integers, so it's bounded below by 0. So the main thing that we got to prove about S is that there's actually something in there. I mean, how do we know that by creating things that look like this, how do we know that any of those things are actually non-negative integers? Well, I think we can demonstrate that there is a value of k that we could pick that will make that expression a non-negative integer. All right, we're going to divide this up into two cases to see what happens when n is bigger than or equal to 0. Well, in that case, let's just pick k is equal to 0. Because if we pick k equals 0, then n minus dk will just be equal to n. And that's in S because it is a non-negative integer. Now it's a little trickier when n is less than 0. The trick here now is to select k to be equal to n. Now let's see what happens. So n minus dk is equal to n minus dn. We factor out the n, and then we get that we have n times 1 minus d. N, in this case, is negative, and 1 minus d is less than or equal to 0, because remember when we started, we said that d had to be a positive integer. So that means 1 minus d has to be less than or equal to 0. Well, if you multiply these two things together, something that's negative times something that's either negative or 0, then you have to get something that's bigger than or equal to 0. And so again, n minus dk is an element of S. Essentially what we've proven is that there is a way to select a value of k so that n minus dk is non-negative. That means that S is non-empty. This was crucial for being able to apply the well-ordering principle. Now, S is defined to be a set of non-negative integers, so it has a lower bound of 0. So, finally, we can apply the well-ordering principle to S, and we can assert that S has a least element, and we'll call that least element R, because it's going to fit the R that we get in the conclusion of the quotient remainder theorem. Now, R has to be bigger than or equal to 0. Why is that? Well, remember, S is defined to be a set of non-negative integers. Now, for some specific integer k, and we're going to call that integer q, we have R is equal to n minus dk. And that's because of what is in S. It's things that can be written specifically in that form. Now, the last thing we need to do is to prove that R is less than d. That was part of the conclusion of the quotient remainder theorem. We're going to do this by contradiction. So let's suppose, for the sake of contradiction, that R is bigger than or equal to d, and we'll see what happens. So then, if I look at n minus d times q plus 1, and work out what that is, I get n minus dq minus d, which is r minus d. That's bigger than or equal to 0. Now, what does that tell me about this number here? That tells me that, first of all, it's in S, and it's also something that's smaller than R. Because how was R created? R was n minus dq. And so this has to be a smaller integer. That would contradict the assumption that R is the smallest integer in S, and therefore we can say that R is less than d. So basically what happens is if R was bigger than d, then we'd be able to go a little bit smaller in the set. So that basically proves the existence portion of the quotient remainder theorem. We'll come back another time and prove the uniqueness portion, that there actually can only be a single value of q and a single value of r that satisfies the conclusion of the quotient remainder theorem. Okay, that's all for now.